So we're going to start a new chapter today called as carbohydrates. Okay. So before we start carbohydrates, okay, being medical students, can you tell me what are the functions of carbohydrates in our body? Where do we find carbohydrates in our body? I know that they're really very, very important part of our body,
Sugars.
right? When we talk about biomolecules, they play a very, very important role in our body. Energy, absolutely. Yes. When it comes to energy, we know that glucose is the most important monosaccharide. Very good. Okay. Anybody else? Metabolism. Yes. Absolutely, Abdulaziz. We will see that in biochemistry when we'll talk about at the end, the various metabolic pathways. You'll see that there are various intermediates of our metabolism, right? Where you will have one or the other carbohydrates. Very good. Storage form of energy. Absolutely, we store them. Very good, Mohammed. We store them in liver and muscles, right? The glycogen, right? Okay, very good. Other than that, where else do you find? What do you think? Where else do we have carbohydrates in the body? So we said energy, we said metabolism, we said storage. What else? That's all? Okay. Anybody else? Something related to the genetics? Have you ever heard the name of ribose and deoxyribose before? Absolutely. Isn't it? If what is your DNA and RNA? Sugar, phosphate, and base, right? So sugar is like everything, right? We we are able to transmit our genes from parents to the next offsprings, right? To next offspring. How? Because we actually transmit the DNA to the next generation. So it's one of the very important constituent of the nucleotide, ribose and deoxyribose, right? Other than that, OS means sugar. Absolutely. OSE means, yeah, we're going to talk about that. OS means sugar, OSE. Aldose, hexose, ribose, right? That's all. Glucose, erythrose, right? That's all. It means sugar. Oh, don't you think so? The structural component. Have you ever heard about the structural component? If you remember the structure of the structure of the plasma membrane last semester we discussed, can you figure out where do we find carbohydrates? Nobody? See, if you remember last semester, we spoke about the receptors, glycolipids, glycoproteins. Where does the word glyco come from? Glyco means what? Glyco means sugar, right? Carbohydrates, isn't it? Absolutely. Okay. So, carbohydrate, right? Uh, Carbohydrates are called as the let me get my pen first. Carbohydrates are called as the polyhydroxyaldehyde or polyhydroxyketone. When I say hydroxy, you'll see that there are many OH groups, okay, in the carbohydrates. Okay, so carbohydrates are basically aldehydes and the ketone compounds. You will either find aldehyde group in the carbohydrates or you will find the ketone group in the carbohydrate. Okay, we'll go on to the structures in a while. Okay, and you will see there are multiple hydroxyl groups, so that is why the word polyhydroxy aldehyde or a ketone compounds. Okay, and that gives the or and once you hydrolyze them, you break down these compounds. Okay, due to the reaction with the water, once you hydrolyze them, right, they might give at least the same thing. Okay, so if we need to write the formula of the carbohydrates, that's how we write it. Okay, Or we can write something like this: CN, then we have H2O N. So this part showing that they are the polyhydroxy aldehydes or the ketones. Okay, and they play a very important role in our body. We just discussed a few functions of the carbohydrates in our body, right? We discussed how important they are as an intermediate in the metabolism. You'll see so many carbohydrates as an intermediate in the metabolism. Glucose, right? We are alive because we are able to oxidize the glucose, right? So that is nothing but it is the carbohydrate structural component, right? Okay, not only in animals, in plants also, cellulose, a structural component, okay, is nothing but the carbohydrate. Imagine there are no carbohydrates, we will literally starve. Can you believe? The food which we eat, the sugar, the flour, whatever, the vegetables, the fiber, all that comes from the carbohydrates. Okay, then we have something called the simple sugars and the complex sugars. Okay, so for example, if you see monosaccharides, okay, if you see here monosaccharides, are they simple sugars or the complex sugars? What do you think?
Simple sugar.
Simple sugars, isn't it? So these simple sugars, you will find them, like they have just one monomeric unit. You will find them in various, candies, jellies. Okay, and then we have the disaccharides, which have two monomeric units. Okay, and for example, when we hydrolyze disaccharides, okay, so how many molecules will it yield upon hydrolysis? Disaccharides, what do you think, if you hydrolyze them? Absolutely true, two, isn't it? What about trisaccharides? Tri will give three molecules, right, on hydrolysis. What about oligosaccharides? Oligo means short chains, right? Like 3 to 10 monomeric units, isn't it? So 3 to 10 molecules will be given, 3 to 10 molecules of monosaccharides will be given, okay, if you hydrolyze the oligosaccharides. And poly, of course, the more than 10. So poly will be considered oligo and poly, right? These two will be considered as the complex carbohydrates. Okay. Can anyone give me an example of the complex carbohydrate?
Insulin.
Anyone give me example of the complex carbohydrate? Any polysaccharide? Glycogen, absolutely. Starch, we eat rice, right? Potatoes, wheat, that's nothing but the starch, right? So we eat fibers, okay? That's again a complex polysaccharide. And in this chapter, we will learn that why we are not able to digest the bonds of the dietary fibers. We'll discuss that, okay? When we discuss the linkages between the sugar molecules, we'll discuss about that, okay? So when we talk about the word aldose, look at this. The word aldose, what does it tell you? What do you
That
get to know when you hear the word aldose? Aldose, that means aldehyde, ketose, ketone group. So that by looking at the word aldose, I can simply make out that there's an aldehyde group in the sugar, and ose is the word for the is a suffix uh, for the sugar. Okay. So by looking at the word aldose, I can say that it is a carbohydrate which contains an aldehyde group. So and aldehyde group is CHO, right? And when I hear the word ketose, I know that there is a ketone group, right? And OSE is the sugar, okay? Like fructose. Fructose is a ketose. It contains carbonyl group, this at position number 2. Aldose, glucose, right? Glucose is so very important. It is an aldose. Similarly, you might hear the word triose tetrose. I don't think they have mentioned triose tetrosis. Triose means what? What can you expect from tri means Three, you'll expect three carbon. Ose means sugar. Right? We'll discuss in a while about glyceraldehyde, which is the triose. Tetrose, how many carbons? Four, right? Aldopentose. If I say aldopentose, what is it? Aldopentose or aldoketose. Sorry, ketopentose. So
Five.
aldopentose and ketopentose. That means five and a ketone group. Aldo, aldehyde group and five carbon. Absolutely, very good. Okay, so hexose, our glucose, our galactose, right? They're all hexose sugars. Okay, so aldoses. Okay, so heptose, the seven carbon. So we'll not go far. We'll just going to discuss up to six carbons. Okay, like this is a table I just brought in here so that you can basically see that like these are the monosaccharides, disaccharides, polysaccharides. So remember the examples. Glucose is present in fruit, fructose in honey, galactose. The word galactose is basically gala. Gala means milk, right? So galactose is present in the milk. Maltose is a disaccharide, glucose plus glucose, present in the barley. Sucrose is glucose plus fructose. Table sugar. Table sugar is nothing but the sucrose, right? Lactose in the milk is made up of glucose and the galactose. And then we have these complex polysaccharides like starch, cellulose, pectin, glycogen. Okay, this we'll discuss at the end of the chapter. Okay, so we just discussed about the ose, triose, tetrose, and the pentoses, hexoses, heptoses. Okay, so there are only two trioses. Okay, and one and both of them have the chemical formula as you can see here, C3H6O3. Okay, and this is a one triose called as a glyceraldehyde. Okay, and another one is the dihydroxyacetone. Both of them are trioses. Okay, glyceraldehyde, once we'll discuss the glycolysis at the end of the semester maybe. Okay, so you'll find glyceraldehyde as an intermediate in the glycolysis. Okay, and once we discuss the lipid synthesis, okay, there you will find this dihydroxyacetone. So at that time you should be knowing that these two are the trioses. Okay, and like these are the only two trioses wherein, if you see glyceraldehyde, you will not find the OSE word, as in ribose, heptose, fructose, right? And then we have the dihydroxyacetone. So these are the only trioses where you will not find the word OSE at the end. Okay, so who will explain this? What kind of isomers are glyceraldehyde and dihydroxyacetone? This is my question to everyone. What do you think?
I think they're
Nobody?
aldose.
After studying the chapter number 14, chirality, nobody's going to tell me what kind of isomers, after studying isomerism, nobody knows what kind of isomers are glyceraldehyde and dihydroxyacetone.
Um,
Before Googling
enantiomers.
it, what do you mean by structural isomers?
Enantiomers.
What are structural isomers? Enantiomers. How come they're enantiomers? Do you think they're mirror images of each other? Who said that enantiomers? Do you think they're mirror images of each other? Are they? Do they even look like mirror images? Here we have a double bond, here we don't have a double bond. How come they're enantiomers? No, no, I can't hear you, ladies. I'm sorry, I can't hear you. No, Hannah. I need to figure out what's the problem. Let me check. What's the issue? My speakers are on. Can someone talk now? Can you please talk so that
Yes, doctor, can
I
you
can
hear
hear
me?
you? I try to fix everything.
Doctor, can you hear me?
Okay, give me a minute. Can we talk now?
Yes, doctor, can you hear me?
Yes, I can hear you now. Thank you, Rand. Thank you, dear. Yes. So no, there was no need to Google it. We never spoke about structural isomers. We used the word constitutional isomers. Absolutely. If you remember, we discussed in the previous chapter what are constitutional isomers. Glyceraldehyde and dihydroxyacetone have same molecular formula. Do they have same connectivity, guys? No, they don't.
Different connectivity.
Different. They even have a different functional group. Here we have an aldehyde, here we have a ketone. So aren't they constitutional isomers? Yes, right? So you need to know all that, right? For enantiomers, it was very important they're mirror images. They cannot be enantiomers at all, right? They're constitutional isomers. That's the next question, Faiza, which is coming up. You have to answer that question. Are they chiral or achiral? Faiza, be ready for the question. So glyceraldehyde is the simplest aldehose and contains one stereocenter. If you look at this, isn't this a stereocenter for glyceraldehyde? Right? I have here one group, I have another group here, I have another group here, and I have another group here. So now, can I say that this one and this one, okay, are they enantiomers? Can I say that? Yes. So are they chiral? Yes. Are they symmetrical or asymmetrical? They are asymmetrical, isn't it? Absolutely, right? So these are the two enantiomers of the glyceraldehyde, right? So yes, they are chiral. Now my question is, what about dihydroxyacetone? Is it chiral? No. Why do you say so? It's not why dihydroxyacetone is not having any enantiomer?
Have double bond.
First of all, there's a double bond, and it's connected to two of the same
Absolutely. Because there's
molecules.
no chiral center. Absolutely, right? Isn't it? We don't have four different groups attached to it, right? Symmetrical. Absolutely. If I look at this one and this one is similar. Very good. Okay. So that's why dihydroxyacetone has no enantiomer. So sometimes some books you will see that they'll write there are three trioses which are available. They call this as we'll discuss that in a while. They call this as a D. We'll discuss what is DNL in a while. Okay, one, two, and this one as the third one. Okay, they consider these two enantiomers as one and two. Okay, so moving on further, we'll talk about the Fisher projection formula. Okay, Fisher projection formula is basically Fisher was a scientist, okay, who actually his name he was a German chemist, okay, his name was Emil Fisher, okay. He gave us a method, okay, based on the projection of a tetrahedral carbon. You see carbon is tetrahedral here, right? So he was tired of using the the three-dimensional formula which we discussed in the chirality chapter previously, right? He was kind of tired of using that because the problem with the carbohydrates is carbohydrates have very striking feature. Okay, they have plenty of stereogenic centers, carbohydrates. Okay, as we'll move on towards the pentoses, hexoses, you will see they have many stereo centers. Okay, so he thought that it's like a very cumbersome job, very difficult to draw all that. Okay, this is in the plane, that is another in the plane, this is in the front, this is in the at the back. So it's very time consuming process. Okay, so what he gave his own formula, a two-dimensional representation of the tetrahedral stereocenters. Okay, and very easy one. He thought like if by using his projection, he said that you can easily count the stereocenters. Okay, so That's why we normally use this Fisher projection formula, because it gives us the information about the stereogenic centers in the carbohydrates, because as I told you that carbohydrates have number of chirality centers. Okay, so this Fisher projection gives us definitely a very handy method, a very quick method, okay, to represent their stereochemistry, and it was given by none other than by the Emil Fisher. Okay, and now this is so very common. If you see every biochemist or every organic chemist, right, they will use, because it was adopted throughout the world. Okay, so they will use, you know the Fisher projection to show the chirality centers. Okay, you know and now what did he say? He said that we simply need, for a tetrahedral carbon, okay, in a Fisher projection, he said that we simply need two crossed lines. Okay, he said that one horizontal line, okay, it will represent the bonds coming out of the page. Okay, so we should not be worried about that, because our basic aim is to find out the stereo centers here quickly with the Fisher projection. So horizontal lines, if this is a horizontal line like this one, okay, it represents the bonds coming out of the page, as you can see here, the solid wedges. Okay, and then the vertical lines like this, okay, represent the bonds going into the paper, right? So 3D thing he showed, on a 2D paper, right? On a two-dimension, he showed for a three-dimensional organic molecule, he gave us a two-dimensional representation, right, on simply a paper. Okay, so this is a Fisher projection for the glycerol day, which is one of the very simplest type of carbohydrates. Okay, so let me show you more complex ones. Look at this. If I have, this is a Fisher projection for the aldotetrosis, ketopentoses. So if you're given structures like this and you're asked, okay, this is like a Fisher projection formula, or you can also even write it like this, right? Like this. So from here, the carbon represents, this is like a carbon 1 from here. Then we move to carbon 2. Then this is carbon 3. Then this is carbon 4. That's how we write the Fisher projection formula. So you can write it this way, or you can write it this way. So if you're given these two sugars, which you see on your screen, how many chiral centers are present in the aldotetrosis and the ketopentosis?
Two.
Okay. Are we are we correct? Two chiral centers, two stereocenters, right? So this would be the one, and this would be another one. So how many enantiomers will be possible for
4.
stereoisomer? Absolutely right. Two pairs. Wonderful, right? Okay, so this is like a Fisher projection formula. Okay, but then he also told us one more thing about, he gave, D and L assignments to the to the sugars. Okay, he said that Fisher said that when you're making, for example, any compound, for example, you make it like this or like this one. Okay, so this represents your stereo center. This represents your stereo center. Okay, so he said that the on the right hand side, okay, if you, this is your, for example, stereo center over here. Okay, he said that the configuration of the stereo center, which is totally far from the carbonyl group, for example, there's a carbonyl group over here, right? If I open it up, so he said the stereo center which is far from this carbonyl group, okay, or the penultimate carbon atom. Okay, if you see on the penultimate carbon atom, if you see OH on the right hand side, he assigned it the prefix D to it. Okay, and if you find that in the penultimate carbon or the stereo center which is far from its carbonyl group, okay, if the OH is on the left hand side, he called them as the L sugars. Okay, so what is DNL? Please remember, everybody, this DNL is totally different from the DNL which we learned previously in the chirality when we were doing optical activity. If you remember, there we said if it's turning the light in the clockwise direction, we call it dextro and levo, right? But that was a small d and small l. Here we write D and L. So what is a DLN configuration? The way we discuss about RNS configuration. So DNL specifically we use for the carbohydrates, and we'll also learn about them in amino acids as well. So D and L are used, which was given by the Fisher. They're used to label the monosaccharides, and they're used to label even those monosaccharides which have many stereogenic centers, because if you remember, I told you that carbohydrates usually have many chiral carbons, they have many stereogenic centers. Okay, I'll give you one more example. Look at this. Which is the penultimate carbon? Like, this is the last carbon. Okay, the carbon, this is called the penultimate carbon. You can say this is a penultimate carbon, or you can say the configuration of this stereocenter, because this stereocenter is very far from the carbonyl group, or this stereocenter is very far from the carbonyl group, right? So he said that the configuration of a stereocenter which is very far from the carbonyl group determines whether the monosaccharide is D or the L. That's what he said. There are many ways to say the same thing. You can either call this as a penultimate carbon. Okay, you can also call it as the highest numbered stereo center. What do you mean by highest number stereo center? If I start, let me erase this. If I start numbering the stereo centers over here, this is my one stereo center, this is my second stereo, this is my third stereo. So the highest stereo center, that is very important. So there are three ways of, kind of assigning, if you have to assign DNL configuration to carbohydrate, to monosaccharides, right? The three ways you can actually quote the carbon atom. You can either say that the penultimate carbon atom, that is not the last one before that, okay? Or you can say the highest numbered stereo center, which is of course this one. This is the first one, this is the second one, this is the third one, okay? Or you can say the stereogenic center, which is very far from the carbonyl group, okay? It tells us whether a monosaccharide is D or it is L. And one thing, I'm again repeating it, this D and L is totally different from the optical active. Like, this D and this L is totally different. They're totally different. Okay. So, and not only that, R and S is also different, right? There are different ways, the different suffixes which we use to, which we use, to name these chiral, or, the stereoisomers. Okay. Do we have question? Is it possible to convert D? So we'll move on later on to that. So that is not our topic, but yes, it is. But we are not, since we are biochemist, okay, we are not. If you want to do that in the lab as a chemist, you can do that. But as a biochemist, for me, what is important for me and for you, what is important, that is all the naturally occurring carbohydrates come in the category of D. Glucose and all other naturally occurring sugars are all D sugars, right? You have to remember this forever. Okay, so in nature, right, if you want to do it in the lab, you can do anything in a chemistry lab, right? But for me, in nature, because we're dealing with the biomolecules, for me, I have only and only D glucose, D fructose, everything is D. And I have L amino acids that we'll discuss later on. Okay, and I'm repeating it one last time, that please don't confuse it with the dextrorotatory and the levorotatory, because you might end up seeing that D glucose, for example, if I have a D glucose, capital D, remember, if I have a D glucose, a D-glucose can be dextrorotated. Like, if you remember, we discussed the plus sign is used for the dextro. Okay. Even the D-fructose, okay, when we say D-fructose, you might think that D means for positive. No, because D-fructose, if you see here, it is levorotatory. Do you understand what I'm trying to say? That's why glucose is sometimes called as a dextrose. All clear? Okay, so yes, please remember that. Okay, thank you. So this was given by Fisher. Okay, uh, this was a method how to label the monosaccharides, because we know that they have multiple stereogenic center. So if you look at this diagram, can you tell me, is it D or L? If you see here, I have OH. This is my penultimate carbon. Okay, or highest stereo center. My OH is on the right hand side, so this becomes D. Here, this is the penultimate carbon. OH is on the left side, this becomes L. What about,
Doctor, I have a question.
yes dear?
Why did they say on the highest numbered stereo center?
I have to ask him, but unfortunately he's not alive. How will I ask him?
So it's not the
It,
highest numbered,
I
or
think it's the highest number. That's what he told us. That makes our life simpler. As we move on, you'll see that makes our life simpler. Because for example, it's question. If you ask me a question like, why did they tell us that if you have to move in the clockwise, it's the R configuration? Why is it, when we go anti-clockwise, it's S configuration? Do you have an answer for that? I don't.
no?
That's why I wish he could be alive. Fisher could be alive. I would ask him this question.
So when we're labeling D or L
Simply make your
groups,
life simple. Make your life simple. We have so many things to discuss. Make your life simple. You see, I give you a molecule. You see OH on the right, it's D. You see OH on the left in the penultimate carbon, say it's the L. Khalas.
Okay, thank you.
Got it? let's discuss the aldotetrose and the ketopentones. What do you think? Aldotetrose, is it D or L? Which is the penultimate carbon here, guys?
D.
Which is right. If you see here, this is my one stereo center, right? This is my another stereo center, right? And this is my like the highest stereo center, right? Or the other way of saying the same thing is like this is my penultimate carbon, and I see OH is on the right hand side, so this becomes my D. What about this one?
Both of them are D.
Absolutely. See here, this is my one stereo center, this is my another stereo center, or the like this is the penultimate carbon. So I have OH on this side, so both of them have the D configurations, isn't it? Abdulaziz, I want you to write capital D, not small d, because small d might confuse you saying that it's dextro. And yes, thank you, dear. Thank you. Both are D sugars. Okay, so did you all understand about D and L configuration? Is there any question about it till now? All clear. Okay. We now move on to the most common tetrosis and the pentoses here. Okay. So if you see here, this is the D erythro. This is the D erythrose. Who will tell me how many stereocenters are present in D erythrose? Let's start with the D erythrose first. How many stereocenters in D erythrose?
Is it three?
Two.
Three? No. In D, how many stereocenters in D erythrose? Two. Absolutely. See, look at this. Don't you find Fisher's projection is a little easier for us? So it's like this is my one stereo center, right? This is my another stereo center. Like this is my one group, this is my another group, this is my another group, and then this whole becomes one group, isn't it? And then we have and then we have the Okay, it's D because if you see here, OH is on the right hand side, right? In D3Os, if you see here, OH is on the right hand side. So all of them are D. If you see in the ribose, this is my like if you want to label your stereocenters, this is my one stereocenter, another stereocenter, three stereocenters here, right? So the highest stereocenter is basically this one. And here I have, or this is a penultimate carbon. I have OH on the right hand side. So this becomes my D ribose. Okay. And here also I have OH on the right hand side. So this becomes my D ribose. What kind of isomers are D erythrose and D3-rose? Who will answer this question? Let me erase this for you. Maybe this will be difficult. Okay, now tell me. Absolutely. Cis and trans, isn't it? Look at this on the same side OH and this is on the opposite side. What is the difference between ribose and 2-deoxyribose? What is the difference between these two? Difference between the two. These two. Mhm. They're not mirror images. They're stereoisomers. They're diastereomers.
Only one group is different.
Yes. If you see here, let's observe the carbon number 2. This is the carbon number 2 in the D-ribose. This is the carbon number 2 in the deoxyribose. So I have here OH and I don't have O over here. So this is the deoxy D-ribose. So this is present in the DNA. Okay. And this one is present in the RNA. Right? So D-erythrose, this one you will find it very important when we will discuss the liver metabolism. Okay, and we will discuss something called the pentose phosphate pathway. Okay, you will discuss how important D-erythrose is there. Okay, then we have this D3-rose. Okay, so D3-rose is basically you'll find it in you'll find it many places in the body. Okay, and it usually has one more stereoisomer, but let me not go into detail. We don't need to know that. Okay, it has uh, other isomers, so let's not go into that. Okay, and yeah, we just discussed ribose and deoxyribose. They are found in RNA and the DNA. Okay, then we'll discuss the three most important hexoses, like six carbon with the which have six carbons. Okay, the hexoses, hexes, six and O's is the sugar. Okay, so these like a very three very important hexoses like D-glucose and D-galactose and D-glucosamine. Okay, and how many stereocenters in D-glucose? Can anyone tell me?
4.
So this is my one, this is my two, this is my three. Now, what do you say? Wasn't Fisher clever enough? He just gave us an easiest way to identify the stereo centers, right, in carbohydrates. Because if you remember, I told you they have plenty of chiral carbons. So this gives us an easiest way to find out how many stereocenters they have, right? And OH is on the right hand side, so this becomes the D-glucose. Okay, and you know how important glucose is for the body. Then we have the D-galactose. Okay, in the D-galactose, which we, as I discussed, that gala means milk, right? So it's present mostly in the milk and the milk products. Okay, and you will find galactose in the nervous tissue as well. It's present in the nervous membrane as well. Okay, uh, and then we have the D-glucosamine. Okay, so we'll discuss that in a while, the amines. Then we'll discuss something called an epimers. What are epimers? Okay, can anyone tell me what is the difference between D-mannose and D-glucose? Observe the structure carefully. Observe these H's and OH's. Compare D-mannose and D-glucose and tell me what is the difference between mannose and glucose. What do you think?
The difference in carbon number two.
Difference in carbon. What is the difference in carbon number two?
We um hydrogen here and OH on the other side.
Okay, so we have hydrogen on this side on the mannose, and here we have, instead of hydrogen, we have the OH here. Is she correct? Absolutely. She is absolutely correct, right? So these two would be called as the stereoisomers. The D-mannose and D-glucose would be called as the stereoisomers or diastereomers because they differ in their configuration only at one stereo center. Okay, if you look at them carefully. I have CHO group, I have CHO group here. Okay, I have H on the right, H on the right, OH on the left, OH on the left, OH on the right, OH on the right, OH on the right, OH on the right, CH2OH, CH2OH. So all, so they are basically similar at every stereo center, but only at C2 carbon, right? Only at this stereo center, they have been flipped. Here we have hydrogen on the right hand side. Here we have hydroxyl on the right hand side. So I can say that mannose and glucose, they are called as the epimers. So when two diastereomers differ only at one chirality center, everywhere else they have same, right? But they differ only at one chirality center, we call them as the epimers. Yes, I know there, don't worry. I will let you know at the end of the class what we're going to do about these presentations. Don't worry. I'm going to upload it. Don't worry. As a revised PPT. Okay. Because let me, I don't want, if, for example, if I upload this presentation there, then I don't want to scare people that, oh my God, we have 72 slides. She gave us such a long presentation. We have to learn so much. I don't want that to happen. So that's why I uploaded the basic presentation, which you already have, okay, which is already uploaded in the Moodle. And just in case, whatever extra I uploaded, I uploaded as a revised presentation. So it becomes your choice whether you want to go with the revised one or with the other one. I will upload both the presentations as a revised one. No, no, no. Abdul Aziz, we need to come out of the anatomy and physiology. We are in a biochemistry class. Okay. So they're called as the epimers. Okay. So what is the definition? The definition, if you see here, everywhere else they are same. They'll all look similar everywhere else, but only at one stereo center there is a difference. We call them as the epimers. So can I say that mannose and glucose, they are the C2 epimers? Can I say that? Yes. So you have to know all this. Okay. So if I give you the structure of mannose and the glucose in the exam, you should know that whether they are C2 epimers and whether they are whatever they are, right? They're always C2 epimers, of course. Let's try to compare glucose and the galactose now. What do you think? What's the difference between glucose and galactose? Let me erase all this so that it doesn't confuse you. Let's discuss now glucose and galactose.
Galactose is complex.
Mm-hmm.
The glucose is simple.
Mm-hmm. Mm-hmm. We're not talking about that. We're talking about epimers.
And carbon number four.
Absolutely. Let's compare glucose. Very good. Glucose and the galactose. If you see here, this and this is similar. This, I have OH on the right. Here also I have OH on the right. I have H on the right, H on the right. I have OH on the right, OH on the right, CH2. Like everything is similar in these two, except at C4 carbon, they have been flipped. In the galactose, I have H on the right hand side. In the glucose, I have OH on the right hand side. So at carbon number 4, they have been flipped. So glucose and galactose are the C4 epimers. Is it clear for everybody? If I ask you a question now, my question comes up. Okay, let me erase this first so that now tell me, is everybody, can you all hear me?
Yes, miss, we can hear
Yeah.
you.
Okay. So what about mannose and galactose? What do you think about mannose? If you, so we compared earlier glucose with the mannose and then glucose with the galactose. Now tell me what about mannose and the galactose? What are galactose and the mannose? Are they epimers?
No, miss.
It is too different. No.
Absolutely. So what are those? What is mannose and galactose? More than one different. Yes, absolutely. I know that. Then so mannose and galactose are not epimers. And what is the other name which we can give to mannose and the galactose? Think everyone. Diastereomers, absolutely, Tanya. Very good. If you look at, if I keep a mirror here, let's say this one is not here, okay, and if I keep a mirror over here, they're not mirror images, of course not, right? Galactose and mannose, they're not mirror images of each other, right? So they fulfill the criteria of diastereomers. Number two, they both of them have same molecular formula. They are not mirror images. They cannot be superimposed. And if you remember, I told you diastereomers usually have multiple stereo centers, right? So galactose and mannose are not epimers, but they are the diastereomers, right? If you look at the position number 2 and position number 4, they are totally different, right? Right? So they are isomer. They are the diastereomers because they are not even the mirror image. So we can't even call them their enantiomers because they are not even mirror images of each other. All okay? Is it clear to everybody? Yeah. Epimer is a type of diastereomer. Yes, Mohammed. Yes. Is a type of diastereomer that has, I told you that when I was defining the epimers, I told you that they are diastereomers, which differ only at one chirality center, right? If you see mannose and glucose, they are diastereomers. Of course, if I keep a mirror in between them, they're not even mirror images of each other, right? They're diastereomers. But at the same time, if I closely look into them, I see that at carbon number 2, the two groups have been flipped. Only at one chirality center they're different. But the condition is, for the epimers, you have to remember two conditions. One, it should be diastereomer. Two, at every other place it should be same as we, when I put a tick mark here, at every other place they are similar, but they just differ only at one chirality center. So that's why I can call them epimers. Is it clear, Mohammed? What was that? Who was that? Mohammed, or yeah, Mohammed. Is it clear, Mohammed, now? The conditions for the epimers? Yes. Okay. Now we'll discuss about the amino sugars. Okay, amino sugars as itself, as you can see here, they contain the amino group, right? So the OH group, one of the OH group is replaced. If you see here, the OH group is replaced here with the amino group. Here it's replaced with the amino group, right? Now, when I say, okay, look at this manosamine and the galactosamine. Okay, find out the what kind of epimers are they epimers or diastereomers? The manosamine and the galactosamine. Everyone, what do you think? These two. Okay, diastereomers, very good, right? Absolutely. And the mannose-amine and the glucosamine, they are the C2 stereoisomers, or you can say the epimers, absolutely, right? So let me erase this. Okay. So we just discussed that amino groups are formed, amino sugars are formed when we substitute what? When we remove one hydroxyl group and instead of that we put a amino group there. Okay. So that's why sometimes they're called as the hexoamines as well. Okay. Because they usually derive from the hexoses. So that's why they're called as the hexoamines. Okay. So for example, D-glucosamine, okay, here we have the amino group as we discussed earlier. Okay. So if we talk about a little bit about anatomy, okay, here where do we find glucosamine? I don't know whether you remember or not. Connective tissue we discussed, last semester, the extracellular matrix of connective tissue, right? Yes, in the extracellular matrix of the connective tissue, we have something called the hyaluronic acid. Okay, you know, so which we find in the, if you remember, we discussed the synovial fluid last semester, right? Synovial joint, synovial fluid last semester, right? Articular cartilages we discussed last semester. It's like, so glucosamine you will find it in the, I was just trying to connect it with the anatomy. So glucosamine you'll find it in the synovial fluid, you'll find it in the articular cartilage. Okay, then we have mannose-amine. Okay, here we have an amino group flipped, right? So these two are the epimers at C2 epimers. Glucosamine and mannose-amine are the C2 epimers, right? And mannose-amine is usually found in the glycoprotein part, right? So when we say glycoprotein, so that glyco is usually mannose-amine. But we have many other as well, but it's like one of those. Okay. Then if you see this one, galactose, okay, galactosamine is basically, which we usually find, in the glycoprotein again. Okay, we recently discussed the FSH and the LH hormone, so you will find galactosamine there. Okay, and then we have the N-acetyl D-glucosamine. Okay, if you see here, we have an acetyl group attached here to the amino group. Okay, and this is a very, very important, N-acetyl D-glucosamine is very, very important part of our cell membrane. It's present in our cell membrane, N-acetyl D-glucosamine. Okay, so that was a little bit about connecting it with the anatomy. Okay, so how many chiral carbons are present in D-glucose, D-pentose, and D-fructose? Who's going to answer? Let's start with the D-glucose. How many chiral carbons we have in the D-glucose?
Four.
Yes, right. One, two, three, four. In D ribose, three, absolutely. What about this one? Fructose.
It is also 3.
One, two, three, exactly. Very good. Do you, okay, you have to remember this thing. If I give you this structure, for example, usually we don't give structures, but we give structures, but not to draw the structures. So if I ask you to identify this, so the fructose has carbonyl group at carbon number 2. Okay, so aldoses have the carbonyl group, or aldehyde group at the carbon number 1. Okay, so the ketoses, the keto sugars, they have the carbonyl group at the carbon number 2. Remember that. Okay, so moving on further, which monosaccharide is known as a blood sugar? Glucose, right? Okay, now we move on to the cyclic structures of the monosaccharides. Now I want all of you to pay attention. This is a little bit, not difficult to understand. I'm sure you'll take care of it, but you just need to pay a little more attention. Okay. So the cyclic structures. Now, why are we talking about the cyclic structures of the monosaccharides here? We have been talking about the linear structures earlier, and suddenly, why did I switch over to the cyclic structures of the monosaccharides? The reason is that we're going to talk about the pentoses and the hexoses only here. Okay, so glucose is a hexose, right? So glucose is like a very important reference molecule. So we'll talk about glucose here, right? So glucose can be represented, if you have to draw the structure of the glucose, it can be represented in the straight chain, as we saw earlier, for example, this. Oh, where is it? This is called the straight chain structure of the glucose. Okay. But then we found that in the biological systems, glucose never exists in a straight chain form. Okay. So this is like an open chain form, okay, or a straight chain form. We found that glucose exists as a ring or in a cyclic structure. Or even there is one more structure called as a chair conformation of the glucose. So a glucose molecule can exist in three forms. It can exist in the straight chain, as we can write it in a straight chain structure. But then we found it in, glucose is more comfortable when it is in the cyclic structure, which we're going to discuss in a while now. Okay. And more comfort level for the glucose is when it moves to the chair conformation. We'll discuss that as well later on. Okay. So open structure was this one, which was given by the Fisher. Okay. And even the open structures, as I said, that it's very important because it gives you, when you just look at the look at the glucose, right, or any other glucose, right, it can straight away quickly give you the stereochemical differences, okay, based on whether the OH is on the right or on the left. But then why we have to know the cyclic structures of the glucose? Because as I told you that in biological systems, we found that monosaccharides, they do not exist as an open chain structure. You might be happy to draw them on your paper, but in biological systems, in our body, they exist in the cyclic form. And those cyclic form are called as the hemiacetals or hemiketals. Acetals, if they have an aldehyde group; ketals, if they have a ketone group. For example, fructose has a ketone group. Now, I want all of you to pay attention. Before I start explaining this, how glucose cyclizes, okay, let's first take just a random example of 4-hydroxypentanol. Now, please pay attention, everyone. I'm talking about how an open chain structure is converted into we call it a Haworth projection. We'll talk about that in a while, okay, or in a cyclic structure, in a ring structure, okay. So let's say this is just not a glucose, it's just anything like 4-hydroxypentanol. Okay. This is an aldehyde, we know that. Okay. So this is carbon number 1, this is carbon number 2, carbon number 3, carbon number 4, and carbon number 5. Okay. And if you see this 4-hydroxypentanol, you will see that it has only one stereo center, isn't it? So this cannot be my stereo center because I have CH3 here. Even this cannot be, I have two H's over here. This cannot be my stereo center because I have a double bond over here. This cannot be my stereo center because I have an H here. So this is only one stereo center here, isn't it? This side I have H, this side I have OH, this side I have this methyl group, and this side I have this whole thing. So this is my stereo center. But I don't want to know the stereo center as of now here. What I need to know is that what happens. Can I redraw this? I will redraw this in such a way so that I will bring my, I want everyone to pay attention, please. C1 and C4 close to each other, because I am interested in reacting the carbonyl group or adding the carbonyl group with this hydroxyl group. That is my aim basically. That is my aim basically. What I'm trying to do, I want to bring the carbonyl group and the OH group near to each other. So if I have to redraw it, I can redraw it something like this. I can keep a carbon 1 here. Then this is my 2 carbon, this carbon. This is my 3, this is my this 3 carbon. This is my 4, this 4 carbon, and this 4 carbon has an OH over here. And then I have the carbon number 5 over here. So by cyclizing it, what I did is I brought this OH and the carbonyl group close to each other. Are we okay till now? Okay. So once I did that, okay, then there's a lot of chemistry involved. I will not go into that because that is not even required here. Okay. Uh, there's something called as nucleophilic attack. I'm not very sure whether you read that. And okay, I don't want to go into, we don't even want to know all that. Okay. In short, just remember that this carbon and this oxygen will form a bond with each other because oxygen is a nucleophile. It will attack the carbon. I don't want to explain the chemistry because then we'll end up the whole period will go explaining the chemistry, and we don't even want to know the chemistry part of it. Definitely when you will learn in chemistry, when you will learn about the aldehydes, right? So this is called an intramolecular bonding. This is like within the molecule itself, the carbonyl group and the hydroxyl group, they form the bond with each other. So there I'm sure that Dr. Amrit will explain you how does a nucleophilic attack takes place. Okay. And how deprotonation takes place. Okay, so we don't want to know that. We just simply want to know that why, when we brought them close to each other, there was a bond which was formed between this carbon and oxygen over here. Okay, and this bond was broken. Okay, the one bond. Okay, and then what happened? And this H went here. Okay, as a result of this reaction, I found something called as a cyclic hemiacetal. Okay, I will explain this with the glucose molecule. It will be further clear with the glucose molecule. This was like any example of an aldehyde. Okay, so what happened when I formed the cyclic hemiacetal? Okay, now if you compare this new thing which I got and compare it with the acyclic one, with the straight one, how many stereocenters were present in 4-hydroxypentanol and how many stereocenters are here now in the cyclic hemiacetal? 2, isn't it? Initially, I had only one stereocenter here, right? Let me erase this so that initially I had only one stereocenter here. But because of the cyclization, because of this intramolecular cyclization, what happened? A new stereocenter was created over here. Look at this. This is my H. This is my OH, different. This is my this part, and then this is my other part. So this is a new stereocenter which was created here. Okay, after doing this intramolecular cyclization. Okay, so it gave a new stereocenter. So this stereocenter is called as the this carbon is called as the anomeric carbon. This one, okay, where the new stereocenter was created. I will repeat it once again. I will repeat it with the, so this is like I just wrote in the definition of the hemiacetal and hemiketal just in case if you want to know that, right? Compounds derived of the aldehydes which are formed by the addition of alcohol and carbonyl group. That's what we did. We added the carbonyl group to the alcohol group, right? It gave us the hemiacetal. And same thing if we do it with the ketones, wherein we add up the alcohol and the carbonyl group, okay? Of the ketones, of course, it will give us the hemiketal. To form this should be ketal, not acetal. Okay. Now let's do it with the glucose. I want all of you to pay attention. This is my open chain structure of the glucose, as you can see here. And I told you that why we are doing this, why we are converting open chain into the closed chain. The reason is that I told you that in biological systems, or glucose prefers to exist as a closed chain structure. That's like a more comfortable position for glucose, and that is how it exists in our body. Okay, so look at this. This is my glucose structure: 1, 2, 3, 4, 5, 6. In order to cyclize, I'll take carbon at carbon number 5. I'll take one hydroxyl group, and the aldehyde group. Remember, in order to do cyclization, we should have a hydroxyl group and we should have a carbonyl group, right? We have a carbonyl group in the aldehyde, right? So the hydroxyl group and the carbonyl group of the monosaccharides can undergo the intramolecular cyclization. Let's see how. Okay, I'm going to redraw it now. Okay, look at this. This is my carbon number 1. Everyone pay attention. This is my carbon number 1, which has a carbonyl CHO. CHO. I can open it up like this. I can write a carbonyl group like this. Okay. And remember, I want to make a reaction with the carbonyl group and the OH group at the carbon number 5. So what I do is, then this is my carbon number 2. This is like this carbon. Carbon number 3 is this carbon. Carbon number 4 is this carbon. Carbon number 5 is this carbon, right? And carbon number 6 is this carbon, which is outside. Now, usually, we don't give you to draw the structure of the Haywood. Usually, we give a question for a biochemist. You should know that how to convert a straight chain into the Haywood structure, okay? So in order to convert that, as I said, that the way I wrote it, you will write it this way, okay? Then there is a tricky part. The tricky part is, how should I write my OHs and Hs? How do I know where should I write my OH and H? Okay, so this is my the 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 OH which you find, okay, on the right hand side. Okay, you're going to write them down. Whatever you find on the right hand side here, you're going to write them down. Okay, and whatever you have on the left hand side, you're going to write them up. Okay, so if this is my carbon number 1, forget about it. This is the OH on the right hand side. Where should I write it? Down. All the right hand side will go down. Look at this. At carbon number 3, I have H on the right hand side. Look at this. Carbon number 3, I will write H over here, down. At carbon number 4, I have OH on the right hand side. Carbon number 4, I will write OH down. Right? And then on the left hand side, whatever I have, I write that up. Okay, so I have H over here. So look at this. My H goes right over here, above the plane of the ring. OH on the carbon number 3 is above. OH on the carbon number 3 is above. H at the carbon number 4 is above. H at the carbon number 4 is above. So whatever you find on the right hand side, you will write down the ring, and whatever you find on the left hand side, you will write up the ring. But the last one, you have to pay attention. In the last one, if you see carbon number 5, I have OH also attached here. I have H also attached here, and I have CH2OH also attached here. So for the carbon number 5, what do I do is, right, we always write the bigger group, the bulkier group, CH2OH, at the topmost position. And then H we write down, the left one we write down, and we write OH in such a way so that we need to make a reaction with the C double bond ONOH. We need to bring it close to each other. And I'm sure that people are lost. Are we lost, guys? Did you all understand? This is just, nobody's going to give you a question how to convert a open chain structure into cyclic one, right? But you just need because it's going to help you maybe in College of Medicine, right? You are lost. I know that. Unfortunately, I'm not in the classroom otherwise. Yes, but no, we're not going to give you a question to how to convert, but you have to understand what I'm doing here. You have to understand that my ultimate aim, this is a mnemonic which I wrote over here. This is a mnemonic because if you are planning to practice it, how to convert a straight chain into the cyclic one. Okay, so we are not, as I said, that we don't need to know that. What is important is that you understand the concept here, what is happening here. The concept here is I'm bringing CHO group, the carbonyl group, and one of the OHs, the OH at the carbon number 5, close to each other so that I can do the addition reaction. That is my ultimate aim. Muhammad, CHO. How do we write CHO? Functional groups, chemistry. CHO is C double bond OH. Muhammad. Remember the revision presentation? Right? CHO, you can also write it this way. C double, yeah, I got it. Okay, wonderful, great. Okay, okay. So everybody, pay attention. So what I'm trying to do is I'm simply bringing the CHO, okay, the carbonyl group, and one of the hydroxyl groups close to each other because they have to make a closed ring structure. That's what happens actually. Okay, so in order to make a closed ring, you need to bring, for example, in aldoses, you need to bring carbon number 1 and OH of the carbon number 5 close to each other so that you can convert an open chain into the cyclic structure. Remember that. Forget about these mnemonics because we are not giving you a you have an MCQ, right? So we are not giving a test wherein how to convert the open chain into the cyclic one. Is it okay? Did you understand the concept till now? Why did I write it this way? The idea is to bring OH and carbon close to each other so that I can do the addition reaction. Clear? Okay. So the same thing, what will happen after that? This carbon and this oxygen will form a bond. Okay. One of the bond will break down. This H will go to this OH. Okay. Look at this now. Okay, so this is a hemiacetal. This cyclic structure is called as a hemiacetal. Okay, so this cyclic structure is called as an hemiacetal. What happens when a glucose cyclizes, when a glucose is doing intramolecular cyclization, that is what is important, which you have to remember that, right? It gives rise either a 5-membered or a 6-atom ring. If you count this ring, tell me how many atoms are in this ring. Is it a 5-membered ring or a 6-membered ring?
6.
It's a 6-membered ring, right? So if this is 6-membered ring, so I will call it a pyranose. And if it gives rise to a 5-membered ring, which we'll learn later on, I'll show you the 5-membered ring. How does it look like actually? If it forms a 5-membered ring, like this is a 5-membered ring, then we call it a furanose. In short, cyclization of the hydroxyl and the carbonyl compounds always and always, right, gives rise to either hemiacetal or a hemiketal. Cyclization of an aldehyde with the hydroxyl group will give rise to a ring structure, which could be either a 6-membered ring or a 5-membered ring. If it's a 6-membered ring, that's very important. You should know it's called as a pyranose. And how did we get to know this is pyranose or furanose? I'll tell you from where did we get this names. So look at this. This is a 6-membered ring which has one of the atom is the oxygen. We call it the pyran. Okay, this is a 5-membered ring. One of the atom is the oxygen. We call it the furon. This is actually an ether, right? But if this type of ring is formed in the glucose, right, or in the sugars, in the monosaccharides, then we call them as the pyranose, OSE. This will be the suffix OSE is the furanose. Are we okay? I'm going to repeat and recapitulate one last time. I said that glucose can exist in 3 different structures. It can be a straight chain structure, it can be a ringed structure as you saw here, and it can also be as a boat chair, chair conformation, which we'll learn later on. Okay. Then I said that glucose in the biological systems is mostly found in the cyclic structure, this cyclic structure, right? So what happens in order to form this cyclic structure? What happens? The carbonyl group of the glucose, I don't want to say glucose. Usually, the cyclization takes place either in hexoses or in the pentoses. Okay, so I gave an example of hexose here, glucose. Okay, so in the cyclization reaction, what happens? The carbonyl group of the present at the C1, okay, will cyclize or will form addition reaction with the with the hydroxyl group of the carbon number 5. While doing so, what happens? There will be a bond which will be created with between O and the carbon. Okay, this bond will be broken. This H will be added here. Okay, so because of this addition of cyclization of the glucose, what happens? There was an additional, you know, asymmetric center created. Okay, this one, this asymmetric center was created here. Okay, and this is called as an anomeric carbon. The way you saw in the previous one, in this one we had only one stereocenter. After cyclization, there was one extra stereocenter created over here, and this extra stereocenter is called as the anomeric carbon. Same thing is with the glucose as well. If you start counting the chiral centers in the straight chain form and count the chiral centers in the cyclic form, you will see that this had only 1, 2, 3, and 4 chiral centers. But if you count here after cyclization, there's an additional chiral center which is formed in the cyclic ring. So this has 1 chiral center, 2 chiral center, 3 chiral center, 4 chiral center, and 5 chiral center. So this chiral center was recently formed after cyclization, and we call it as the anomeric carbon. So you have to know all that. So this is like which is very important. So if somebody will ask you that, what is an anomeric carbon? How will you respond? What is an anomeric carbon? How will you respond? What is an anomeric carbon? Guys.
The new stereo center that was created using the cyclic way.
Yes, you can say that the closure of ring created a new stereocenter or a new chiral center at C1. Okay, that carbon is called as the anomeric carbon. Okay, so as a result of this carbon, this new stereocenter formation, you will see that it will lead to the formation of the two isomers in the glucose. One is called as the alpha D glucopyranose. Everyone, please pay attention. I know it's difficult, but if you pay attention, it will be easier for you. I will repeat once again, don't worry. So because of the cyclization reaction, it gave rise to two different isomers of the glucose, which we call as the alpha D glucopyranose and beta D glucopyranose. Now please pay attention. Now remember this. What is an alpha D glucopyranose? What is beta D glucopyranose? Okay, you have to remember that now. When I say alpha, remember that alpha means where the OH is on the what? OH is on the, can anyone guess that? In the alpha, how is the absolutely in the transposition? If you see here in the alpha, one OH is here, and this is my anomeric carbon, right? One OH is here and one OH is here, right? So this becomes my alpha, okay? Or if you see the OH is in the transposition. And why do I call this isomer as a beta D glucopyranose? If you see here, the OH and this OH, they are on the same side, or cis, right? So we call it the beta D glucopyranose. I know it's difficult to understand, but you need to pay attention, right? So now if I have to open up this, if I need to open up what is beta, what is D, what is gluco, what is pyranose. So beta, when the OH is on the same side, I call it a beta. If I give you this compound in the exams and ask you, please identify this. So the moment you see OH is OH on the same side, so you will first of all say, oh, this is beta. Okay. Then you know that D is like, we always know that D is, in the biological system, right? We all have D glucoses, right? So if you see here, OH was on the right hand side. So that is why I use the word D here. Why gluco? Because it's actually glucose, right? It was an hexose sugar, right? So it was a glucose. So that's why the word gluco. Why pyranose? Because after cyclization, it formed a six-membered ring. So that is why the word pyranose came here. Is it clear? Now, I think I had given one mnemonic here. You know how to remember? I give a mnemonic here. The mnemonic is, if you see OH in the trans position, in the trans, you have A in between, right? If you see OH in the trans position, if I give you this structure, so it will be easy for you to identify this is alpha. So trans is A. Remember that, alpha on the opposite side. Clear? And if they're on the same side, use the word cis. So remember, the word trans has A, so that means it is always alpha. Trans is always alpha. Remember that. Okay, or the other way, because in biochemistry it's all about mnemonics. Biochemistry is all about, you cannot remember things unless and until you create your own mnemonics. Or for example, when I learned my biochemistry, how I had learned that, how did I remember that in the in the alpha D glucopyranose, OH is in the down, because I know that what I remembered is that alpha is for ant. Ants, like, you might find it silly, like ant, and ants always walk on the ground. So in my alpha, I have OH on the downside. And if I give you this structure, how do I know this is beta? Okay, because birds always fly in the sky, right? So in the beta, the OH is in the sky, in the top position. Like, that's how I remembered when I learned my biochemistry. So ant, OH is on the downside. So that's your alpha. Okay. And if you find OH at the top position, and someone will ask you, is it alpha or beta? So you say that if you see OH at the top, so, birds are at the top in the sky, right? So it's your beta. Is it clear, guys and girls? I know it was
Clear,
like
doctor.
difficult not to crack, and it was equally, difficult for me to teach, online this, but I tried my best, and we spent a lot time. I had to finish a lot more things. Yes. Okay. So these new isomers which were formed, like alpha and beta, we call them as the anomers. What do we call them as? We call them as the anomers. Okay. So what are anomers? Stereoisomers that differ in the configuration only at the anomeric carbon. Remember this anomeric carbon? Let me erase this. Right? If you see here, this isomer and this isomer, right? They are two stereoisomers. They differ from each other only at this carbon. You will see rest, everything is same in them. CH2H, CH2H same. H here, H above same. OH below same. OH above same. H below here, H below same, right? Everything is similar in these two isomers, but they differ from each other only at the C1 carbon or the anomeric carbon, right? So that is why we call them anomers. mers. At the C1 carbon, we have OH in the down position, but in the other isomer, we have OH at the top position, right? So this will be called as an alpha, and this, or sometimes we just don't even use the word pyranose. We simply use as the alpha D glucose and beta D glucose. We don't even want to make it long, right? The pyranose and all. Is it clear, everyone? And now I want you to practice this at home, and then we'll do with the furanose. We'll not go into detail with the furanose because it's the same thing again in furanose. And I think hopefully we should be able to finish this in the next class, the chapter. We are kind of lagging behind.